So I want to find the extreme value of this function on this interval. And I'm just going to stop for a moment and think about my function and my interval at a glance. This is a closed bounded interval. That's good. That's what we want for the extreme value theorem. Let's think about this function. This is a polynomial. It is continuous everywhere, so it's continuous on our closed bounded interval. That's wonderful. That means from the beginning, we know that there is an absolute min and an absolute max of this function on this closed bounded interval. And now we just have to find them. So in this case, for these kinds of problems, the strategy is really straightforward. You just locate the critical points, and then you make a list of critical points and endpoints, and you compare. So let's do it. This is easiest to learn by example. So we're going to compute the first derivative, and we're going to get what? 12x cubed minus 12x squared minus 24x. You can pop a 12x out. I'm going to go and factor the quadratic that's left. I get x minus 2, x plus 1. Maybe pause the video, check that for yourself, make sure you can get there. And so the point is, it's easy to see that the critical points are just the zeros of f prime. So where is f prime 0? It's 0 at 0, it's 0 at 2, and at negative 1. So these are x equals 0, x equals 2, and x equals negative 1. And I just want you to realize at this point, you're essentially done, other than just plugging and chugging some points here. So I like to make a little table, something like this. It doesn't have to be perfect, but I've got x, f of x. So I'm interested in the critical points 0, 2, negative 1. And I'm interested in the endpoints negative 2 and 3. And I'm going to plug my critical points into my function. So this is x, plug it into f, not f prime, just f. So I plug 0 into f, I get out 0. I'll do the computations for you here. I plug in 2, I get out negative 32. I plug in negative 1, I get out negative 5. Negative 2, I get out 32. 3, I get out 27. And so quite literally at this point, you're just going along and you're looking for the largest y value and the smallest y value. So the largest one is here at 32, and the smallest one is at negative 32. And so you are essentially done. You should write up your solution, though, in a neat, coherent sort of way. Remember, mathematics is half about correct computation and the other half about correct and clear communication. So we want to go ahead and communicate clearly. We can say, thus, f has an absolute max of f of negative 2 equals 32, and an absolute min of f of 2 equals negative 32. Couple of comments. I could have said absolute max of 32 at x equals negative 2, but I said all of that with a lot less writing by saying it this way. There's the x value, there's the y value, x value, y value. Just to be clear, I got 32 as the max because it is the largest number on this little table. And I got negative 32 as the absolute min because it's the smallest number on this little table. One other comment, you'll notice that in this problem, I did not use the first derivative test. I didn't try to classify these as local mins and maxes. If you want to, you can. It turns out that 0 is a local max. There's a local min at 2, and there's a local min at negative 1. But none of that matters when it comes to finding the extreme values of this function on this interval. You just need the critical points and the endpoints. And notice that one of the endpoints ended up being an absolute extrema, and then one of the critical points ended up being an absolute extrema. Maybe the absolute extrema will be just the endpoints, or maybe they'll be just critical points, or some combination thereof. Anything can happen on these problems. So that's an example where we actually used the extreme value theorem. It applies here, and we knew at the beginning that we're going to find both an absolute min and an absolute max. Let's do one more of those before we go on to some more interesting type problems.